Good evening, morning, afternoon, Calculus Advanced. I'm just gonna follow along in your packets, take some notes, and next class we'll just get a little bit of practice doing it. Okay, so um, let's start. We're gonna jump down here. Average velocity. This is something that you've done before. It's just finding the slope between 2 points. Um, the change in y, which is your position, which is your height or distance, over the change in time, whatever your two times are. We're going to look at an example right here and apply that formula real quick to find the average velocity over an interval of time. So a billiard ball is dropped from a height of 100 feet. The height of the ball, h, at any given time, t, is given by this function. The height according to time is negative 16t squared plus 100. So to find the average velocity from 1 to 2 seconds, we're going to use this function, slope formula right here to find the average rate of change. We're going to take the height at position 2, whatever that is. All right, after 2 seconds minus the height after 1 second over 2 minus 1 second. So the height after 2 seconds, if we plug 2 into this function, 2 squared is 4. 4 times 16, I think 64. And 100 minus 64 is 32. And then h of 1, if I plug 1 to this, is just 100 minus 16, which is 84. 2 minus 1 is 1. So 32 minus 84 is negative 48. And so it went negative 48 feet in 1 second. So that's feet per second. So the average rate when the ball was dropped from this height, from second 1 to second 2, the average velocity was negative 48 feet per second. From 1 to 1.5 seconds, the average velocity is going to be the height, the difference in the height, so how far to travel, over how much time that went by. And again, that's that formula right there. So h of 1.5, if you plug 1.5 into this formula, the output is 64. So after 1.5 seconds, it's 64 feet. So I don't know, 64 feet after 1.5 seconds. Minus after 1 second, you plug 1 and we get 84 still. So now we divide that by 1.5 minus 1 is 0.5. So 64 minus 84, that's negative 20. So it's negative 20 feet. Oops. Negative 20 feet over the course of a half a second, which is negative 40 feet per 1 second. Okay. So that's the average rate of change between 1 and 1.5 seconds. The average rate of change between 1 and 1.1 seconds, well, what was the height after 1.1 seconds minus the height after 1 second? That tells me how far it traveled. Over how much time? 1.1 minus 1. So h of 1.1 is about 80.64 minus h of 1 is still 84. And 1.1 minus 1 is just 0.1 seconds. So that comes out to be negative 33.6 feet per second. So what's going on here is the velocity is negative, which makes sense because the object is traveling downward. So downward velocity we're going to consider negative in terms of height. The height's decreasing, so it makes sense that the rate of change is negative. And what we're doing here is the interval from 1 to 2 seconds, 1 to 1.5 seconds, 1 to 1.1 seconds. We're getting closer and closer to the rate of change at exactly 1 second, and that's what this is right here. What about the exact velocity at a given moment? So the instantaneous velocity is the change in position over change in time as that interval of time gets smaller and smaller and smaller. So this looks familiar. Determining instantaneous velocity will be as simple as finding the derivative. So that's what this looks like, right? And this is the derivative limit definition just with application of position and time. Of the position equation. Okay, so if you want to find the velocity of an object and you know the position, then we can do that just by taking the derivative. So if I were to call p, instead of h of t, I'm just going to call p of t the position function. P of t is position as a function of time. Let's change up the color here. Let's do a nice light blue. So if p of t is the position function and v of t, we'll call it the velocity function. So velocity as a function of time. Then if I take the rate of change of position, which is the derivative, that's how we find a function that tells me velocity. So the rate of change of position, if you go back up here, is feet per second, which is a rate of change, feet per second, feet per second, feet per second. Those are all velocities. So as feet per time changes, that's what we call velocity. And it makes sense that the derivative then of position should be velocity. So whenever we have a position function, and sometimes we'll use h instead of p for height, velocity is just taking the derivative of that function. So a billiard ball is up from that height of 100 feet still, and the height of the ball h at any given time t is this function. What is the velocity function here? So the velocity function, which is the derivative of the height, derivative is green, we just take the derivative of this function, which is just going to be negative 32 t. And that's how we can find the derivative, the rate of change of this. So if I wanted to say what's the instantaneous rate of change at 1 second, so what's the exact velocity at 1 second? Is v of 1, which is negative 32 times 1, which is negative 32 feet per second. So at 1 second, it's going exactly negative 32 feet per second. And these numbers were getting closer and closer to that negative 32 feet per second. As the interval got smaller and smaller and smaller, the velocity got closer and closer to the instantaneous velocity, which was negative 32. Okay, so this is a height equation specifically for this situation, but the general equation for height of an object thrown, so anytime like you shoot a basketball or kick a soccer ball or shoot a bow and arrow into the sky, it comes down. It follows this parabolic path. You may have seen this equation before, but in general, we'll call the height equation h of t is going to be 1/2 gt squared plus v sub 0 t plus h sub 0. And what do each of these things mean? T is going to be time, since the object was thrown or dropped. G is the acceleration due to gravity. Which is always going to be negative 32 feet per second squared. So if you're in feet, that's what we're going to use. If we're in meters, then it's going to be negative 9.8 meters per second squared. So depending on the problem, just look if it says feet or meters. If it's feet, G is negative 32. If it's meters, it's 9.8. So in this problem up here, we were in feet. So we would have been using negative 32. So if I do 1/2 of, so if I do the half of gt squared, half of negative 32 t squared would be the negative 16 t squared, which was used in this problem right here. Anywho, v sub 0, or v naught, as some people call it, is the initial velocity. Vertical velocity to be specific. So being thrown straight up or straight down. Okay, and h sub 0 is the initial height. In the last example, the initial height was 100, which is where we're seeing this 100 here, which is h sub 0. V sub 0, since the ball was dropped is the keyword, its initial velocity was 0. So this part was just 0 in this problem. That's why you didn't see that V sub 0 t. Okay. Example 1. A boy loads a slingshot and shoots a pebble with an initial velocity, vertical velocity of 20 feet per second from the top of a cliff 12 feet over a creek. I think before we answer questions about it, how long will it take for the bell to hit the water, etc., let's draw it. So we have a boy standing on a cliff, and he's got a slingshot. So here's a slingshot, pulls back the rock and shoots it, but he's shooting it up actually. So shoots the rock up, and it'll eventually come down and hit the ground. And it happens to be going over a creek, I guess. So here's my water. Okay. So a couple of things we know. Let's have a diagram. He's 12 feet over the creek, so his height is 12 feet. Sorry if my drawing isn't good. We have his initial vertical velocity is 12 feet per second, or excuse me, 20 feet per second. How long will it take for him to hit the water? So in this case, we're in feet per second. So, well, let me write the actual function that we're looking for here. The height is 1/2 gt squared plus my initial velocity t plus my initial height. So g in this case, because we're in feet, is going to be negative 32 feet per second squared. The initial velocity is 20 feet per second. In the initial height, he's 12 feet over the water. And, we're going to assume that, maybe it's like a little more than 12 because he's probably not shooting it right off the ground, but we're not going to incorporate that here. Okay. So let's put that into the function here. So height is 1/2 of negative 32, which is negative 16 t squared. My initial velocity is 20. And my initial height is 12. Again, this negative 16 came from doing half of g, and half of negative 32 is negative 16. Just know that first term is always going to be negative because it's going, when you shoot something to the air, it goes up and then down. So it's always going to end up going down. That's the end behavior. Okay. How long will it take for the pebble to hit the water? So I want to find out what t is. Let me do this in a different color. So find t when it hits the water. So that's when the height is 0. So when h equals 0. So when the height is 0, solve this equation for t. So a lot of ways we can go about this. You can immediately go into tossing into the quadratic formula. What I'm going to do first, because it'll just make the numbers a little bit smaller, is these are all factors of 4. I'm going to divide both sides by negative 4. The reason why I'm choosing negative 4 so that front term is positive. You don't have to do that, but I just like to do that. So I get 0, negative 16, t squared divided by negative 4 is positive 4t squared. 20 divided by negative 4 is negative 5t, and 12 divided by negative 4 is negative 3. So quadratic formula. Let's do, what's a good quadratic formula color? I don't think purple is it. Let's go orange. So to find the time, it's going to be negative b. So remember, this is going to be a, b, and c. Negative b, which double negative is going to be a positive 5, plus or minus the square root of b squared. So negative 5 squared is positive 25, minus 4 times a times c, which is negative 3, all over 2a. 2a is still 4. So that's going to be 5 plus or minus the square root. Let's see, 4 times 4 is 16. 16 times 3 is, I think it's 48. 16 times 3. Yep. The double negatives are going to make it plus 48, so 25 plus 48. All over 2 times 4 is 8. If you guys have the program in your calculators, just use a program. So 5 plus or minus the square root of 48, 58, 68, 73 over 8. So this is going to give me two solutions, t plus the square root of that over 8 and t minus the square root of that over 8. So we're going to get two answers. One of them is going to be negative 0.44, and the other one is going to be about 1.693 seconds. So what is the answer to the question? How long will it take the pebble to hit the water? It's one of these, and it can't be the first one because you can't have negative time. So that means the right answer is this one right here. So find t when h equals 0, so t equals 1.693 seconds. So the pebble is shot up into the air, hits the ground at 1.693 seconds. How fast will the pebble be traveling when it hits the water? So we're looking for a speed now. If I want speed, I'm going to have to use the derivative to get velocity. So if I want the velocity, that's going to be the derivative of the height. So if I take the derivative of my height function right here, I'm going to get negative 32t plus 20, and the derivative of 12 is just 0. So how fast is it when it hits the water? So we need to find v of t when it hits the water, which we know from the previous question is that it's going to hit the water in about 1.693 seconds. So if I plug that into this function, piece of cake. So the velocity at 1.693 seconds is going to be negative 32 times 1.693 plus 20. And we got negative 34.176 feet per second. So it makes sense that the velocity is negative. And that's it. When will the pebble be at its max height? So when the pebble is shot into the air, when is it going to hit this point right here? So one thing I know about this point is when it's at its max height, the velocity, which is the rate of change, is 0. So what we need to do is find out the velocity equals 0. So we want to set v of t, which is negative 32t plus 20. That's the velocity. We want to set it equal to 0. So I can add 32 to both sides. 32t to both sides. Divide both sides by 32. And so 20 over 32 is 5/8, which is about 0.625 seconds. Right? So it hits its max height at about 0.625 seconds, and it hits the ground at 1.693 seconds. So it should hit its max height before it hits the ground. So that checks out. What's the maximum height of the pebble? So if I want to find the maximum height, we got to use the height function. So we want to find the height when it maxes out, which is right here. So I'm going to find the height at 0.625 seconds. So my height function we have right here still. Negative 16 times t squared plus my initial velocity times t plus my initial height. And we're just going to plug in 0.625, 0.625. Keep it all color coded. So the height at 0.625 seconds comes out to be about 18.25. So So that's its maximum height. So it was shot 12 feet off the ground, and it got to a maximum height of a little more than 12 feet. I don't want to make it look too nasty, but this height right here, the max height is about 18 and a quarter foot. Okay. So those are some questions that you could see using these vertical motion problems. Let's look at example 2 now. Jack and Caroline are standing at the top of the Eiffel Tower, which is 1,063 feet tall. Jack drops his ice cream off the top of the tower. 2 seconds later, Caroline notices that, and not to be outdone, Caroline hurls her ice cream down at what initial velocity such that the 2 ice creams hit the ground at the same time. So what's going on here is we have the diagram here now. So we have the Eiffel Tower. Here's my Eiffel Tower. And Jack threw his ice cream down. And Caroline's going to throw her ice cream down, but his has got a head start. So she has to throw hers fast enough so that they both hit the ground at the same time. Okay. So let's see what's going on here. Both of them were in feet, so gravity is negative 32. Now let's talk about Jack first. Jack, Caroline are off the Eiffel Tower, which is 1,063 feet tall, so that's the initial height. Is 1,063. Jack drops his ice cream, which means his initial velocity is 0. He didn't throw it down; he dropped it. Okay. Caroline didn't drop it. Caroline, we're trying to find out how fast she had to throw it, so we're looking for initial velocity is what we're looking for, so that it hits the ground at the same time as his. Her initial height is the same, though. And her gravity is the same. We're still negative 32. So the strategy is to find when Jack's ice cream lands, then find out what initial velocity Caroline's going to need for her ice cream to land 2 seconds later. Because that is when she decides to throw hers. Okay? So if I'm going to use the height function, h of t, I'm going to put a j here for Jack. So this is Jack's height function. Half of the gravity is 16, so it's negative 16t squared. His initial velocity is 0, and so 0t, which I don't need to write, plus the initial height. That gives me Jack's height equation. Caroline's, I'm going to use C for Caroline's height function. It's still going to be negative 16t squared plus whatever her initial velocity is times t plus her starting height, which is 1063. And this is what we're trying to find in the end of the problem. How fast does she need to throw it? So how long did it take Jax to first hit the ground? Well, to find out when that happened, we want to find out when he hit the ground. So when does his ice cream land? That's when the height is 0. So when h equals 0. So 0 equals negative 16t squared plus 1063. Add 16t squared to both sides. Divide both sides by 16. And square root both sides. And so we're going to get t is going to be plus or minus 8.15 seconds. We don't need the negative here because in the context of the problem, the time's got to be positive. So this is when Jack's ice cream lands. So Jack's ice cream lands at about 8 seconds. So Caroline has to wait 2 seconds later. So she needs her ice cream to land 2 seconds quicker. So, meaning Caroline needs to hit the ground. Needs to hit the ground. Her ice cream needs to hit the ground in 2 seconds quicker, so in 6.151 seconds, right? Because she wants them to hit at the same time. Because Jack had a 2-second head start. So, all right, let's find out when that happens. So, we want to find the initial velocity so that h of this time right here, so after the height after 6.151 seconds hits the ground, so is 0. So we want the height to be 0 when t is 6.151. Okay. And so this is the variable that we're trying to solve for. And this is just a linear equation. Simplify this, add it to the other side, divide, simplify this, or combine like terms. The numbers are nasty, but solving from here should be pretty straightforward. And so then we get the initial velocity is approximately negative 74.401 feet per second. No calculus for this problem. This was very much just kind of like algebra 2 stuff, except getting the velocity. Or no, we didn't need the velocity function. We just needed the initial velocity. So we had 2 people throwing things down. So we have 2 height equations. We wanted to find out when Jack's hit the ground, which is in about 8 seconds. Caroline then, because she has 2 seconds later to throw it, must hit the ground after 6 seconds. So if I plug 6 into her height function, I get this thing right here. And I want to find out what velocity I'll take for the height to be 0. So we solve that. We get negative 74.401 feet per second. Okay. All right. I know it's taking a little while. 2 more examples. And the reason why I want you guys to do this at home is just because these problems just take a lot of practice. So I just want to spend the next class all doing practice problems rather than listening to me do it. And you guys can kind of like re-listen to this when needed. So, in a moment of frustration, an unnamed calculus student hurls their book out of the 3rd floor window to the ground below Waterford High School. The book was thrown upwards with an initial velocity of 22 feet per second from a height of 65 feet. How long will it take for the book to hit the ground, and how fast will it be traveling when it actually does hit the ground? Okay, so someone's throwing their book out of the building, and they're throwing it upwards, so the initial vertical velocity is 22 feet per second. It's positive because they're throwing it up. So imagining you're standing on the 3rd floor of the school, and you throw your calculus book up, and then it's going to come down. So however tall the school is. The initial height, or so the height of the 3rd floor is 65 feet. So we'll call this 65. Keep going. How long will it take? So we're looking for time to hit the ground. So that's when the height is 0. And how fast will it be traveling at that moment? And so we want to find v of t, comma, when we hit, or when the book lands. Okay. So my function here, we can build a height function here. We're in feet again, so it's going to be half of, so gravity's negative 32. So half of negative 32 is negative 16 t squared plus my initial velocity, which is 22 t, plus my initial height, which is 65. So you want to find out when it hits the ground, so that's when the height is 0. Quadratic formula. And then we get my two values of t. What do I get? You get about negative 1.442. And you get t is about 2.817. And again, this one we got to throw out because we can have negative time. So this is going to be the time we're going to use. So now we want to find the velocity when it hits the ground. So in 2.817 seconds, it hits the ground. So how long will it take for the ball to hit the ground? 2.81 seconds. Now I want to find out what's traveling. So that's the velocity. If I want to find the velocity, we just got to take the derivative of the height. The derivative of the height is going to be negative 30. So this is the height. The derivative of that's going to be negative 32t plus 22. So I want to find the velocity when it hits the ground. So that's the velocity in 2.817 seconds. So it's negative 32 times 2.817 plus 22. And what do we get here? We get about negative 68.144 feet per second. So that's how fast the velocity is when it hits the ground. Okay, and that answers how fast. Check. Okay, so that answers the two-part question there. And now, last but not least, Mr. Florio, standing below, finds this to be strange. Decides to toss the book back up to the frustrated student. Naturally, he is a good mathematician and wants to use the minimum vertical velocity. Therefore, how fast should he throw the book such that the book makes it back to the student in the third floor? So I am standing on the ground right here, puzzled by this book I found that says calculus. I know the third floor is right up here, and I want to throw the book back to the third floor. Now, if I throw it over and have it come back down, it's too much velocity because I want to use the minimum. Minimum velocity. Mathematician wants to use the minimum vertical velocity. Let me highlight that. So what I want to have happen is I want to throw it in such a way where it peaks right there. You know, it could come back if there was no building there and the person missed it, it would come back down. But I want the peak of my throw to be at the top of the building. Okay, so so I want my height to be 0. And I'm on the ground. All right, so let's find out what's going on here. In this case, gravity is still negative 32. Now, my initial height, I'm on the ground, so my initial height is 0. I'm looking for my initial velocity, so how hard do I need to throw it? And yeah, let's see what that looks like. So my height function is half of negative 32, which is negative 16 t squared, plus my initial velocity, which I don't know what it is, times t, plus my initial height, which is 0, so I don't need that. So here I have an equation with a t, an h of t, and a v. So there's 3 variables here. We're going to have a hard time solving that. So what else do we know? Well, I want my height to hit 64. Excuse me, it's a 65. This is the height of the building. All right. So we want the height to be 65. So I can set this equal to 65. Now the one thing that, so first of all, there's two variables here, so I'm not going to solve it. Second of all, I want the minimum velocity to be at this point. So what I want here, let me just kind of continue this like I did before. So in order for that to happen, at this moment in time, so at this moment, I'm just going to call it t. For this to be the max height, the velocity at this moment, the vertical velocity needs to be 0. So the rate of change of that function, or the slope, we have to have a horizontal tangent line, has to be 0. So what does that mean? So we want h of t to equal 65 when v of that same t equals 0. So v of t is equal to the derivative of the height, which if I use my height equation here is going to be negative 32t plus v sub 0 t. So I want this to be 0. So 0 equals negative 32t plus initial velocity t. So I need my velocity to be 0 at the same moment that the height is 65. So what we just constructed here is a system of equations. So we have equation 1 and equation 2, and these are at the same moment. The velocity is 0 when the height is 65. So well, that's what I'm saying here. So h equals 65, which I'm seeing at equation 1. And at the same moment, we have equation 2, the velocity is 0. So we have system equations. I want to solve them. What I'm going to do here is solve one of the equations. Let's see. What I can do to clean this one up is if I add 32t to both sides. Just clean it up a little bit. I get that. Where is that t coming from? The derivative has no t. That's where I was making a mistake. So if I take the derivative of this, the derivative of negative 16t squared is negative 32t, and this is some constant times time. So the derivative of some constant times t is just that constant. So that was a mistake. So I can solve for initial velocity by adding 32t to both sides. So what I can do now is take this 32t, which is equal to my initial velocity, and plug it into that equation right there, so that now there's only one variable. So 65 is equal to negative 16t squared plus my initial velocity, which is 32t. Again, initial velocity is 32t times time. So 65 equals negative 16t squared plus 32t squared. Negative 16t squared plus 32t squared are like terms. That's just positive 16t squareds. So divide both sides by 16. And take the square root of both sides. And we should get t is about plus or minus, but again, we're only going to need the positive one, 2.016 seconds. If I want to find the velocity, so I need what velocity will it take to throw it at a height, to throw it at a max height of 65 feet. Let's use my velocity equation. So the velocity after 2.016 seconds is going to be, it's right here. Where's my velocity function? Negative 32 times t plus my initial velocity. Oh, excuse me. I see what I'm doing. So in 2.01 seconds, we want to find the initial velocity. So just use this equation right here. 32 times that velocity, actually that 32 times the time, which is 2.016 seconds, equals my initial velocity. So that comes out to be about an initial velocity of 64.498 feet per second. All right, guys, that's it. Have these notes. You're gonna refer back to them. I know it's gonna be a long break before you see this again or see me again, but I just want you guys to have this now. Sorry it took so long. We'll just get some more time practicing these type of problems. All right.